Hello, grade 12 learners, and welcome to our physical sciences session. My name is Themba Ngube. This is your live broadcast session, proudly brought to you by Pagama Research and Development in collaboration with the Free State of Department of Education. So our focus today, coming back from the well-deserved break that has been, congested with a lot of teaching and learning activities, you must be geared and well ready for our final stretch towards our preliminary examinations, which are going to take place very shortly. So we're only left with 4 weeks before the start of the prelim exams, which says to us we certainly do not have the luxury of time. However, under the circumstances, we also want to reflect on the performance that we had for the June exam with an intention, to try and improve where we could have gone wrong. So we shouldn't despair insofar as our performance is concerned. We still can change a lot between now and the time that we sit for the trial exam. So this is by far the most important part of our grade 12 calendar in terms of us trying to get ready for the prelim exams. Now today we'll be focusing our attention on the physics, which is your electricity and magnetism, with a special focus on electric circuits. Now, speaking of electric circuits, you'd remember very well that this concept of electric circuits are by no means new to us. We have been doing as far back as grade 10 as far as the physical sciences is concerned. So let's quickly dive into the objectives, or what is it that we aim to achieve by the end of today's session. Right, we must be able to state the Ohm's law in words. So remember, the emphasis is on state. So our action verb says state. So to state, it's all about remembering. So it's either you know the Ohm's law or you don't. And remember, we have been applying the Ohm's law from grade 11, right? So that says to us, we are able to remember what the Ohm's law talks about. We'll look into that as well. And then we have to be able to determine the relationship between current, voltage, resistance at constant temperature. So the constant temperature is a very, very important condition for Ohm's law to be true, right? So here we're talking about ohmic and non-ohmic conductors, right? So this is for ohmic conductors, right? So if a conductor is ohmic, it means it obeys Ohm's law. That's what it means, okay? And then we must able to solve problems, okay, involving internal resistance in circuits in both series and parallel networks, or a combination of the two, okay, which is often the case, right? And then we must also be able to solve problems involving electrical power, right? Remember, power is something that we would have done when we looked at mechanics, in terms of rate at which work is done. But here we'll look at calculations or problems involving power in the context of electric circuits. Right. So that's a very, very clear objective. Now, the exam guideline is by far the most important document that we have to pay attention to, relating to remembering, stating, defining, and listing, whatever concept. So here, the Ohm's law is stated clearly in the exam guide. It says the potential difference across. So potential difference, in other words, is the voltage, right? The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. So any resistor, any material that obeys Ohm's law, we call them the ohmic conductors, or a conductor that obeys Ohm's law is referred to as an ohmic conductor. Okay, right. We've spoken about the relationship, the difference between ohmic and non-ohmic. So ohmic obeys Ohm's law. Okay, this one obeys Ohm's law, right? while the non-ohmic does not obey Ohm's law. Okay. Okay, right. And then the Ohm's law is therefore says R is equals to V over phi I. This is in the context of a series parallel circuit. We shall look at a maximum of 4 resistors in a combination. Right. But then also important, we'll look at the concept of power with respect to rate at which work is done. So we remember that P is equals to W over delta T. So in other words, if we've got 1 electrical watt as the unit, this means 1 joule of work is done per second, right? And then when does an electrical component do work in a circuit? It does work because we appreciate the fact that work is energy and energy is work. So when is work done? If energy is the capacity to do work, then work is done when energy is transformed from one form to the other. Say we've got a light bulb that is glowing or that is on. Now what happens is it gives us light energy, but that light energy comes from somewhere. It comes from electrical energy. So the light bulb, in its function in a circuit, it converts or transforms electrical energy into light energy. So when 1 joule of electrical energy is converted to light by a light bulb, the light bulb does work. Right. So one watt of electrical power is equals to 1 joule of energy per second. Right. And then there are the 3 variations. We'll look at the formula sheet or the data sheet to talk to those different formulae. All right. So we'll also solve problems involving concepts of power and electrical energy, right? Then also the cost of electricity, something which is quite relevant in our context with the load shedding very, very prevalent of late. So energy consumption or rather saving of energy becomes a very, very important aspect of our everyday life. So we need to link that with what we learn in class, right? Okay. And then internal resistance series parallel networks. Okay, so we'll look at internal resistance. So we must be able to solve problems involving current, voltage, resistance in a series parallel combination, right? Then define EMF as the maximum energy provided by the battery per unit charge passing through it. Now let's break this down. The battery or the cell, okay, there it is, and then we connect a voltmeter across, right, the terminals. Now what this battery does, we refer to it as a source. Okay, now the term source is used quite often. What do we mean when we say a battery is a source? Remember, it is a source of chemical potential energy that can be transformed into electrical energy. So the battery does work on the charges. So it says voltage from grade 10, voltage is equals to work done per coulomb of charge. Right. Let's say this battery has a EMF of 9 volts. Right. What does that mean? It says that this battery provides, so 9 volts is equals to 9 joules of energy supplied by the battery for every coulomb of charge. Therefore, this is 9 joules per coulomb. Now, this is the maximum. So while the circuit is broken like that, right? And then let's say for argument's sake, we've got a light bulb, and then we've got an ammeter there, right? There is our circuit. Now, if you study that circuit and we ask ourselves, let's call this switch S1. So switch S1 is open, okay? It means the circuit is broken or it is incomplete. So when the circuit is broken, what that says to us is that the battery as a source does not do work outside itself or out in the external circuit. What that simply means that the ammeter reading will be 0 amperes, right? And then the voltmeter reading is what we call the EMF reading. So EMF is the maximum energy provided by the battery per unit charge or per coulomb of charge. A unit, it's 1 coulomb. Okay? So EMF becomes therefore the maximum, right? So while the battery is not doing work, it measures the voltmeter across the battery, measures the EMF. Then if, say, for argument's sake, we close switch S like that, then there's an ammeter reading. So the battery does work inside and outside. Inside itself, because it has got what we call internal resistance, provided we don't ignore that internal resistance. So the battery does work inside itself, okay, this which we call V internal, okay, and then also the battery does work outside, which is the external circuit, which is V external. So now if you add both V internal and V external, you must get the EMF. We'll talk to that in more detail. But then the voltmeter reading, when the battery does work outside, then that's the terminal potential difference, which is what we call V external. All right. Okay, let's speak to these concepts. Very, very important. In grade 10, we spoke about most of the items on the right-hand side, right? All these formulae, we spoke to them in grade 10, including this one. And then this was grade 10, right? And then here, we did this in grade 11, okay? As well as this is the new concept now that we want to revisit, but it's in many ways linked to everything that is shown on the formula sheet, right? So the data sheet becomes a very, very important, aspect of our concept, so that we understand what we're talking about, right? Now, if you want to determine the total resistance of n resistors connected in series, we just add them as shown in that formula, okay? And then for any two resistors that are connected in parallel, this is the formula that we use, or you can say, remember, R parallel is equals to product over sum, which is R1 times R2 over R1 plus R2, okay? And then you remember very well that work is, because we know that V is equals to W over Q, then we know that W becomes V multiplied by Q. This is the work done per coulomb of charge, right? And then the Ohm's law speaks to that very, very important equation, right? So that's our Ohm's law, okay? Right? So the data sheet has quite a lot of information that we can actually get from, so that we make sense of a lot of the concepts insofar as electric circuits are concerned. Right. Now let's talk about the internal resistance of battery. I think the name or the term itself, internal, it says it is the resistance inside the battery. Right. Now, if you come to think of it, we know that R series is equals to R1 plus R2, right? Plus for n resistors in series. Fine. And then what else do we know? We know that a battery possesses chemical potential energy. So as it does work, it transforms chemical potential energy into electrical energy, right? So this resistance is inside the battery, right? Let's color it red. It's inside the battery. That's the resistance inside the battery. Now, then let's say this was a circuit. I'll open the switch there, okay? Let's call that switch S1, okay? And then let's say we've got another resistor external, okay? And then let's say we've got an ammeter there, right? Then we connect a voltmeter across the battery, right? So the voltmeter reading is the maximum reading here. Why? Because when there is zero current, which is 0 amperes, the battery does not do work in the external circuit. So the reading of the voltmeter connected across the terminals of the battery will give us the EMF. So this is the EMF if it's like this. So this will be the EMF reading. Okay? Right. Now, and we know that E is equals to I R plus R. Okay? Before, let's look at the fact that Ohm's law says V is equals to I R. So EMF is the voltage. Current is current. Then in the first part, this one does not take into account the internal resistance. But if we take into account the internal resistance, check, the current that passes through resistor R is the same as the current that passes through the internal resistance. So resistor R external and the internal resistance are connected in series. So our total resistance, that's why it's R plus R. It comes from that fact. Okay, because the internal resistance of the battery is in series with the external resistance. Then if we multiply current resistance with current, we must get the maximum in this case, which is the EMF. That's where the equation E is equals to I, R plus R comes from. Okay, right. Having said that, if we close switch S, okay, we choose to close switch S, what's going to happen? The voltmeter reading, let's call that reading V1, is going to decrease. Why? Because the EMF is equals to IR plus IR. I've just distributed the current. And we know that V is equals to IR. So where there is IR, this is V external, because the external resistance is capital letter R, plus IR is also V. But which voltage is this? Internal voltage. Okay. So let's say our EMF in this case was 9 volts. What that simply means is that 9 volts is the highest reading that we'll ever get in the circuit. Okay? Having said that, therefore we can go on and say, if that's the case, it means the 9 volts is split between V external and V internal, because the external resistance of the battery is in series with the internal resistance of the battery. It means these two resistors in series are going to divide or split the 9 volts. That's what it exactly means. So if we close switch S1, V1 reading will decrease. Now if V1 has a reading, that V1 becomes our V external. Then if we say 9 minus that reading of V external V1, when switch S is closed, we can get the V internal. So the internal voltage is actually the difference between the EMF and the terminal potential difference. So V external, in other words, is the what? Is the terminal potential difference. Okay. Now, and then their difference, therefore, gives us what we call the internal voltage, which is sometimes in some books it will be referred to as the lost volts. All right. So that's the concept around internal resistance of a battery. And the internal resistance of a battery is in series with the external resistance. That's why we add them. It comes from that fact, resistors in series is their algebraic sum. Right. Okay. I hope that makes sense. Right. Now, we want to use the following activity to try and recap on the pre-knowledge that we did in grade 10 and 11. And remember, in grade 11, we also introduced the concept of internal resistance with an intention to say, come 2024, we will just try and revise that and consolidate the concept so that you actually understand what it's all about. Right. So work with me. We are going to give each other a chance to do, to respond to routine calculations and definitions, just to try and, recap. So take this activity as, a practice one. So we'll try and go through it together, step by step, so that we can guide each other. Right. Now it says here, in the circuit represented below, two 60 ohm resistors are connected in parallel. Okay. And then there is another one of 25 ohms that is connected in series. Right. The battery has an EMF of 12 volts and an internal resistance of 1.5 ohms. Right. Now, before we look at the questions, let's study the circuit and ensure that we actually understand it. Right. The 60 ohm resistors, let's call the first one, let's call the 60 ohm R1, and then this one, let's call it R2, and then the 25, let's call it R3, resistor 3. Right. Now, R1 and R2 are identical resistors. Okay, I'll repeat. R1 and R2 are identical resistors. What do we mean? We mean that the resistance of R1 is equal to the resistance of what? R2. Right. Then what else do we know about R1 and R2? They are connected in parallel. So R1, okay, these effects, R1 and R2 are current dividers. Okay, that's fact number 2. What do we mean when we say R1 and R2 are current dividers? When we trace the circuit from the positive terminal to the negative terminal, this is what comes up. When the current gets there, what happens? It is split. Okay, it is split. Okay, I'll change the color wherever there is a split. Okay, that's a split. And then when it gets there, the current is then just a moment. The current is there for I just want to change the color once again so that we can trace it. Then when it gets there, it becomes red again. So wherever there is red, it means it's the total current passing through that. Wherever there is blue, it means the current is split. Right. Now, if we have done that, we understand that the voltage across R1 is equal to voltage across R2. Even if R1 was not equal to R2, we know that in a parallel circuit, current is divided, voltage remains the same, irrespective whether R1 is equal to R2. Even if they were not equal, identical resistors, their voltage, because they're connected in parallel, was going to be equal. Right. And then we know that the total current passes through, the current passing through the battery will pass through R3. So R3 is in series. Right. So current for R1 plus the current for R2 is equals to the current passing through R3. Now it means the total current passing through R3 is split between the current passing through R3. Okay, so the current through R3 equals to the sum of the current of R1 and R2. Excuse me. And then what are we saying? We are saying that the total voltage in the circuit is split between V parallel. So V total is equals to V parallel plus V across R3. Parallel, we mean the V of 60 and 60. All right? Now, then this is indeed a true example of what we call a series parallel or parallel series combination of resistors. And what is also very important for us to note is that EMF is given. E is equals to 12 volts. Now, what do we mean when we say the battery or the source has an EMF of 12 volts? What that symbol says to us is that this battery can supply a maximum of 12 joules of energy for every coulomb of charge. All right? In other words, the 12 volts suggests that it's 12 joules of energy per coulomb of charge, or 12 joules of work done for every unit charge. Right, that's what it means. And then in this case also, we're given the magnitude of internal resistance, which is 1.5 ohms. Right? It's also given. So there are two things to note here. EMF internal resistance can be given, or may be given, or may not. Or we may have one of them. Whatever the case, it's not a train smash. But also take note that you have to try to understand the circuit. So the exercise that we've just done up to thus far is a clear demonstration of what it means when you say study the circuit and understand it before you answer the questions. Right. So what are we saying here? We are saying here the two resistors R1 and R2 are in parallel. Now, the first question says calculate the equivalent resistance of the parallel combination. It's 3 marks. Okay, I'll give you 2 minutes to try that. So if it's 3 marks, remember, it's formula, substitution, and answer. And the answer must have the correct SI unit. So I'll give you 2 minutes starting from now, then we'll do the feedback. Let's try that for now. Welcome back, grade 12. I'll ask you to stop for now so that we can quickly reflect. So we said if a routine calculation problem has got an allocation of 3 marks, it means it's a formula. You copy the formula from the data sheet, substitute correctly, and then write the correct answer, including the correct SI unit. Right. So now, having said that, okay, let me go back a bit. Okay. All right. So we want to calculate the equivalent resistance of the parallel combination. So the parallel combination is R1 and R2. Okay, we'll come to all right, this. Let's say we know that our R1 is equals to 60 ohms, and then our R2 is also equals to 60 ohms. So these are two identical resistors because they've got equal resistance. So we know that we can use R parallel is equals to product, which is R1 times R2 over sum, which is R1 plus R2. So R parallel is equals to 60 times 60 divided by 60 plus 60. Okay, so R parallel, if we go to your calculator, or 60 times 60 divided by 60 plus 60, which is 120, the sum, then R parallel is equals to 30 ohms, right? So if you go to the formula sheet, it will say 1 over R parallel is equals to 1 over R1 plus 1 over R2. So 1 over R parallel is equals to 1 over 60 plus 1 over 60. So 1 over 60 plus 1 over 60, 1 over R2 is equals to 2 over 60. 2 over 60, 2 over 60. Now remember, the mistake that many of you would most likely commit is to leave the resistance as a reciprocal of the parallel resistance. So this is RP, sorry, that's R parallel, okay? So if you cross multiply, it will be RP is equals to 60 divided by 2, which means R parallel in this case is equals to 30 ohms. Now, the effective resistance of any two resistors that are connected in parallel must be smaller than the smallest resistor. Okay, let me explain what I mean by that. Let's say R1 was, for argument's sake, 10 ohms, and then R2, let's say for argument's sake, was 5 ohms. Now, if these two were connected in parallel, their equivalent resistance R parallel must be less than the smallest resistor. It must be less than 5 ohms, which explains why 30 ohms is the equivalent resistance of the two resistors in parallel if it was 60, 60, and 30 is indeed less than 60. That's what we mean. So that's one way of checking whether your calculations are accurate, right? Okay, let's go back to the problem itself. Okay, and then it says calculate the total current in the circuit. Calculate the total current in the circuit. What do we have? We've got EMF, we've got internal resistance, we want current. But remember, R parallel, we have calculated R parallel. R parallel is the 60 and 60 combination, and then R parallel, we have found that it is 30 ohms. Right, we are looking for current. Okay, calculate the current, total current in the circuit. Okay, now I'll give you 3 minutes to try to calculate the total current. So if it's 5 marks, it says this is a multi-step type of a problem. So it's not your straightforward substitution, formula substitution and answer. It means we have to find something first, then use that something to determine the final answer in this case, which is the total current. The total current is the current that passes through the battery. So I'll give you 3 minutes to try and calculate the total current, knowing that the parallel combination of resistors for R1 and R2 is equals to 30 ohms. Your 3 minutes starts from now. All right. I'll ask you to stop now so that we can do some bit of feedback on the question which involves the calculation of current. We are given the voltage, which is the EMF. We have calculated the resistance for the parallel combination of resistors, and then we're looking for current. Right. Let's go to our solution. Right. So we know that E is equals to I R plus R. Right. Now the question is with the total resistance. Total resistance is, which is the external resistance, is equals to R series plus R parallel. Right. R series is 25 ohms plus R parallel, which is 30. So we get an R total of 55 ohms. Right? Now that's the first part. Okay. Now we know that E is 12 volts. We're looking for current. Now this is 55 plus 1,5. 1,5 is given as the internal resistance, right? And then we know that we want to isolate the current there. So it will be 12 divided by the sum of 55 and 1.5, which is 12 divided by 56.5. Okay. This gives us what? 0,212. 0,21. 2 decimal places, amperes. Right. So this is the total current in the circuit. So if we can go back to that circuit, you realize that the current passing through the battery, let's say here we had an ammeter. Let me put an ammeter. It will read 0,21 amperes. Right. So this is the total current that goes through the parallel resistors there. Right. Now the question says we want to determine, let's call this 3.1.3, the potential difference across the parallel resistors. So in other words, this is what we are looking for. It's V parallel, right? We'll try and do V parallel together so that we can try and make sense of it. Now, we know the current that goes through both of those resistors. So the formula for 3 marks, the formula is V is equals to I R. All right. Okay. So the V parallel in this case will be the current across the parallel, which is the total current 0,21. All right. The total resistance for the parallel combination, which is 30 ohms. Right. So we have got 0,212 multiplied by 30. Okay, what do we get? We get 6,37 volts, right? Okay, 6,37 volts. Right, there's something that I want us to prove here, right? It's 0,37 volts. This is V parallel. So let's write there 6,37 volts, right? Okay, there's something that I want us to prove. Very, very important concept that I want us to prove there. Okay, never mind the heading. So E is equals to 12 volts. That's one. Okay, now we know that V parallel is equals to 6,37 volts, right? Now I want us to determine V across R3, right? It's equals to current total, because all the current passes through R3, multiplied by the resistance. Okay, so VR3 is equals to I total is 0,21 amperes, R3 is 25 ohms. So V across R3 is going to be 0,21 multiplied by 25. Okay, this gives us 5,25. 5,25. 0.25 volts, right? And then let's determine V internal. We know that V internal is the total current because it passes through the internal resistance of the battery multiplied by the given internal resistance, right? So V internal is equals to 0.21 multiplied by 1.5 ohms, right? This gives us what? 0.21 plus 1.5, okay? Or multiplied 0.21 multiplied by 1.5, okay? This gives us 0.315 volts, right? Now, if we add, we know that E is equals to what? E is equals to V external plus V internal. So, but the V external in this case becomes our V external is equals to our total current multiplied by our external voltage according to Ohm's law. So our total current is 0.21 multiplied by 55. Okay, you remember the 55 is V parallel plus it's R parallel plus R series. Then if we calculate that 0.21 multiplied by 55, what do we get? We get 11.55 volts. That's our V external, right? Now, if our V external is 11.55 and then our V internal is 0.315. Okay, due to the rounding off, you'd realize that if you add 5.25 plus 3.75, this gives us our V external. So 6.37 plus 5.25, it gives us 11.62, okay, which is exactly that V external after rounding off. So this is actually what gives us what we call the external volt, the EMF, which is equals to the maximum reading. So in other words, V external of 11.62 is actually split between, so this is 11.62 if we did not round it off, 11.62. This is our V external, okay, which is split between V parallel and V series, okay? Why? Because the external resistance and the internal resistance are connected in series, right? And then this is what we would refer to as our V internal. So it's true when it comes to the Ohm's law that indeed in a series circuit, voltage is divided and current remains the same. All right, now let's go back to that particular problem so that we can bring some meaning and context to it. Right. Okay. Right. Now, for this circuit, I think we've managed to, if you look at the number of marks there, it's about 11 marks in total, excluding the definition. So if there was a definition, it means this takes us to what, 13. And these are 13 marks that anyone can actually manage to get. Right. Now, before we go to the next practice activity, what I'm going to do is I'll allow us to take a 5 minutes break. Then after that, we come and continue with our more circuit problems. But after the break, we want to look at circuit problems that involve electrical power, as we had indicated. Let's take a breather for now. from our short breather. Let's hope you're ready and looking forward to the next segment of our very very exciting session, so to say. Now, let's look at a context where we have got resistors, which is both parallel and series with a little bit of complexity, a little bit, but based on grade 10 and 11 work, we must be able to actually make sense of the scenario, right? We've got 3 resistors, 2 ohm, 4 ohms, and Rx. So Rx, the resistance of Rx is unknown. Let's put a question mark there. It's connected to the battery, switches are open. Okay, the voltmeter reading with switches S1 open and S2 closed. Okay, S1 is open, S2 closed. The reading on the voltmeter is 10 volts. Okay, with both switches closed, the reading on the voltmeter is 8 volts. Okay, and the ammeter is 1 ampere, right? So now it means if the switches S2 is closed, if we close here, this reads 10 volts. Okay, now let's put this into context. What is this 10 volts? This is because while the switch is open, when switch S is open, this is 0 amperes. So the maximum reading when there is no current in the circuit is the EMF, the maximum reading of the voltmeter connected across the battery. So let's get that from the fact that E is equals to 10 volts. So a battery can supply a maximum of 10 joules of energy for every unit charge, and a unit charge is equals to 1 coulomb, right? And then if we close the switch, okay, if we close the switch like that, if with both switches closed, we've closed both switches, the voltmeter reading V drops to 8. Therefore, it means V external is equals to what? 8 volts. Now, then what is our V internal? We know that E is equals to V external plus what? V internal. It means our V internal is 10 minus 8, which gives us what? 2 volts. Right. Now, if the ammeter reading is 1 ampere, if the switch is closed, okay, we forget about that. And then it means we can be able to determine the internal resistance of the battery, because now we know how much of the internal voltage we have. So it's 2 volts. So that 2 volts V internal comes from the fact that we multiply the current and the internal resistance that we don't know, right? So 2 is equals to 1 multiplied by R. So the internal resistance of the battery is equals to 2 ohms, because it comes from 2 over 1. So what are we doing here? We are studying the circuit, right? So that we understand it. Now, having done that, now we know that from the circuit, EMF is 10 volts. V external is 8 volts. V internal is 2 volts. The internal resistance is 2 ohms, right? This is what we've derived from the information, right? And then we know that the total current given, because all the current passes through that, is equals to 1 ampere, right? Now let's look at the questions. It says, write down the value of the EMF of the battery, right? It doesn't say calculate. The instruction says write down, and then it's 1 mark. Okay, so it means from starting the scenario, you must be able to make sense of what an EMF reading is. When do we get an EMF reading? Let's go over that once again. The EMF reading is obtained when we connect the voltmeter across the battery and there is 0 current in the circuit. That's the EMF reading. However, that's not the definition of what EMF is. What is EMF? Let's go over it once again. EMF is the maximum energy supplied by the battery for every coulomb of charge. So the maximum that can be supplied here is what? It's actually 10 volts, right? Then what is the terminal potential difference? terminal potential difference is actually the V external, okay? It is the work done by the battery outside. That's why we call it voltage external for V external. So V external plus V internal, which are in series, gives us the total voltage. So we know that in a series connection, what happens to voltage? It is divided. So the 10 volts is divided between the internal voltage of 2 volts and the external voltage of 8 volts. So the 8 volts is not only the terminal potential difference, but it is the V external. Okay, that makes sense. So if it says write down, we have already done this. Okay, so if it says write down, you just answer directly. So this is going to be 10 volts. That's the maximum reading. Now we're going to calculations. Calculate the resistance of the unknown resistor. Okay, first things first, let's go back to our circuit. Let's appreciate that this V across that unknown resistor, okay, let's call it Vx, and this, okay, let's call it V parallel. For us to get V parallel, we must know what is our R parallel. That's the starting point. And if we go back to the question, this is 7 marks. 7 marks, what does it tell us? It's a multi-step. Okay? Problem. So now we're addressing the technique as well. This is a multi-step problem. For us to get resistor, the magnitude of resistance X, Rx, we must first of all determine the R parallel. So we already know that for any 2 resistors in parallel, we can use R parallel is equals to R1 times R2 divided by R1 plus R2, okay, which is product over sum. So R parallel therefore becomes what? 4 times 2 over 4 plus 2, right? 4 times 2 is 8. 4 plus 2 is 6. So this is 8 over 6, which is 1.5, 1.5 ohms. Okay. Now, 1.5 is less than 2 ohms. This is exactly what we said earlier. The effective or the equivalent resistance of any 2 resistors connected in parallel must be less than the smallest resistor. Now, let's go back to the scenario. The smallest resistor is 2 ohms. It means for 2 resistors of 4 ohms and 2 ohms connected in parallel, their effective resistance must be less than 2 ohms, which is exactly in this case 1.5 ohms. I hope it makes sense. Right. Now, we have found a 1.5 ohms as our R parallel. So we are able to find V parallel. Right? We are able to find V parallel. So V parallel is equals to I total multiplied by R parallel. Okay? So our V parallel, in this case, the total current of 1 ohm, 1 ampere, is split between 4 ohms and 2 ohms. Now, are these 2 resistors identical? Not anymore. So it means, yes, we want to appreciate that even though they are not identical resistors, their voltage, the voltage across each one of them is the same, because we have made an understanding that is clear to say that for parallel resistors, the voltage remains the same. Okay? Now, the total current is 1 ampere. Their effective resistance is what? 1.5. Okay? So V parallel is equals to 1.5 volts. So if this is 1.5 volts, what is Vx? We know that the 8 volts is split between 1.5 and split between V parallel and Vx. So Vx is actually 8 minus 1.5, which gives us what? 6.5 volts. Okay, 6.5 volts. That's Vx. So now that we know that this is 6.5 volts, why are we saying Vx is 8 minus 1.5? Because we are saying the external voltage in its total is 8 volts, right? If the external voltage is 8 volts, then it means that the 8 volts is split between V parallel and Vx because they are in series, right? So now if we know Vx, that Vx is 6,5, then we are looking for Rx. How much current passes through Rx? 1 ampere, right? So we know that Vx is equals to what? I times Rx, right? So we have Vx now, which is 6,5, right? We have the current, okay, which is 1 ampere. Then we can find Rx. So it means Rx is 6,5 ohms. So Rx is equals to 6,5 ohms, right? So if we go back to the question, then this is 6,5 ohms, right? Okay. And then now we want to find the internal resistance of the battery. So Rx is equals to 6,5. We also have the EMF, which is E is equals to 10 volts. Okay. We also have the internal resistance, which is, if we can go back, the internal resistance is 2 ohms, right? So the internal resistance is equals to 2 ohms. Then we are supposed to determine, if we have found the internal resistance already, because we know that we can simply say, even to prove that E is equals to I, okay, R plus R, right? So our E is 10 volts. Our current is 1. Then our total resistance, in this case, if we go back to that circuit, we have got Rx, we found Rx to be 6,5, and then that one to be 1,5, the V parallel. So 1,5 plus 6,5, this gives us 1,5 ohms plus 6,5 ohms. That's our R external. Okay, 1,5 plus 6,5 gives us 8, okay, ohms, okay, plus R, okay, right? So if you say 10 divided by 1 is 10 minus 8, you get R is equals to 2 ohms, which is exactly what we have proven initially when we said V internal is equals to total current multiplied by internal resistance. Our internal voltage is 2 volts, right? Is equals to 1 ampere multiplied by R. So our R is equals to 2 ohms. So whichever way you choose to do it, it will basically work out to the same solution, right? Okay, I hope that makes sense. Okay, so the total so far of marks is 11, and these are 11 marks that each and every one of us can actually get as long as we understand the work, right? How will the reading on the voltmeter be affected if the switch S1 is closed while S2 is open? How will the reading on the voltmeter be affected? S1 closed, S2 open. Let's go back to the circuit. S1 is closed, okay, S2 is open. So if we open S2, we are taking out the 2 ohm resistor. Now, what does that effectively do? If we take out the 2 ohm resistor, it means the effective resistance of the circuit will increase. So first things first, before we talk about, because V1 is the V external, let's get that right, right? V1 is the V external. So we know that E is equals to what? I R plus I. Let's get this right. So we know that EMF remains constant for a battery, right? So that horizontal line means not changing. So if we remove the 2 ohm resistor, the V external, the R total resistance increases. Number one, effective resistance increases, okay, because we have less resistors in parallel. So if effective resistance increases, what happens to V external? Okay, V external increases. If the total resistance increases, it means the battery does more work outside, right? Then what must happen to internal voltage? And then because the current decreases, when we increase the effective resistance outside, current decreases, okay? Current decreases, and then V internal decreases. Okay, so if this decreases, that must increase. That's always the case. More effective resistance outside, it says that the battery does more work outside because there's greater resistance. Now, also increasing the resistance outside, what effect does that have on the current? The current is going to decrease. Once we decrease the current, it means our V internal must also decrease. So while V external increases, V internal decreases so that EMF remains constant. So these questions are very, very important in terms of explanation. So if you check, there are 4 points there or that we have actually listed. But the key thing is that V external increases, R external increases, V external increases, current decreases, and V internal decreases. So the sequence which we have also put those facts is something that is very, very important. So you start by arguing to what does that change do to the external resistance? More resistance external, less current. Less current, V internal decreases, and then V external increases. That's why the terminal potential difference is going to increase. And the terminal potential difference is actually our V external, right? So this is a very, very good question in terms of application, right? Now I want us to take a turn and look at a different circuit as we would know it, say from our grade 11 work. It says here there are 3 resistors and an electrical device rated 16 watts, right? So for any electrical device that we use at home, there is always a power rating. Let's take for argument's sake, a speaker, okay? A speaker that is 800 watts, right? Versus a speaker that is 1,000 watts, okay? Both are resistors in the sense that these 2 electrical components transform or convert electrical energy into sound. But what is the difference exactly? The 800 watt, what it does, it transforms 800 joules of electrical energy to sound in 1 second, while that one of 1,000 transforms 1,000 joules of electrical energy into sound in the same period of time. So if it transforms electrical energy into sound per second, it is actually doing work, because energy is the capacity to do work, and energy cannot be created or destroyed. So 800 watts is same as 800 joules per second, while 1,000 watts is 1,000 joules of work per second. That's why the 1,000 watt speaker is more powerful. So the power is with respect to how much work is done per unit time. So in a unit of time, we've got 1 second. Okay? So I was just trying to explain that. So 16 watts means 16 joules of work done per second. Right? They are connected to a battery of EMF 36 volts. EMF is 36 volts. It is given. So E is equals to 36 volts. What does it mean? This battery can supply a maximum energy of 36 joules for every coulomb of charge. That's what it means. Okay? And then the internal resistance is unknown. It's R. Okay? It's shown in the diagram. The ammeter A2 reads 2 amperes. Okay? There it is. Okay? Now it says define the term EMF of a battery. So the term is not EMF. Okay, we need to qualify it. EMF is EMF of what? It's EMF of a battery. It's not a word, it's a term. Okay, So the exam guideline, it will say define EMF of a battery as the maximum energy supplied by the battery for every coulomb of charge or for every unit charge, right? So the term is EMF of battery. So always refer to the examination guidelines. So the examination guidelines will specifically say you must identify the keywords in a definition, and the keywords must also be used in the correct context. What are the keywords? The term maximum, okay? The term maximum. So if we can go back to the exam guideline, I think we can easily remind ourselves of what is important. It says bullet number 2. Define the term EMF, okay, of a battery, ne? EMF of a what? Of a battery. We're talking about the source as the maximum energy provided by the battery per unit charge passing through it. So this is what is worth 2 marks. Okay. So even if we can go to the mark allocation, we would see that it says 2 marks there. Okay. So maximum energy supplied by the battery per unit charge or per every coulomb of charge. Right. Also, before we go further, let's study the circuit and make sure that we understand it. Okay. We're going to trace the circuit from the positive terminal to the negative terminal. Okay, that's our positive because that's the direction of conventional current. Okay, when the current gets there, okay, what happens? When the current gets there, let's change the color. We get the blue there. Okay, right, the blue. Okay, and then when it combines there, we get the red again. Okay, let's take it back to the red. So where there is red is the total current passing through it. Okay, that's the total current back to the battery. So the total current passes through the battery. The split current is the blue, right? Now we're told that A2 reads 2 amperes. Now is 2 amperes the total current or the split current? It is the split current. So a current of more than 2 amperes passes through this 2 ohm resistor A1 and the battery. So A1 measures the total current in the circuit. Right. So that's what we understand. Okay. Now all the current will pass through the 2 ohm resistor. Right. Now the first question says calculate the resistance of the electrical device. It's 3 marks. What is 3 marks for? Formula. Okay. Substitution. And then what? Correct answer, which must include the correct what? SI unit. So that's 1, 2, 3 marks. That's how we get 3 marks. So let's go back to the circuit. We want the resistance of the electrical device. Okay. From the power formula, if we go back to our formula sheet, very, very important. In grade 11, we know that P is equals to what? VI, okay? But what do we have? We have got the power, we've got the current, we're looking for resistance. So we're forced to use P is equals to I squared R. Okay, let's go back. Okay, so the resistance of the electrical device, P, which is the power, electrical power, is equals to what? I squared R, right? Now, that's formula mark, okay? We have the 16 watts, okay? Do we have the current passing through the electrical device? Yes, it is the 2 ampere, it's blue in color. So it's 2 squared multiplied by R, okay? 2 squared is 4. 16 divided by 4 gives us 4. So R is equals to 4 ohms, okay? Can verify that, okay? So this is 4 ohms, right? So that's formula, substitution, answer. And the answer correct includes the correct SI unit, right? And then now for 5 marks, calculate the current passing through the battery. Now this is 5 marks. what does that tell us? This is a multi-step problem. Okay, it means we have to find something, okay, and then use that answer in determining the final solution, right? So we want the current passing through battery. Okay, now if we can go back, okay, we want the current passing through the battery, which is the main current. And remember, if we are able to find the total current in that, we can also find the what you call the voltage. So the voltage for 8, this is 12, because this is 4 plus 8, right? If this is 4 plus 8 is 12, it is parallel to what? To the 10 ohm. So the voltage across this series combination, let's call it R12 ohms. Okay, the 12 ohms comes from the 4 plus 8 is equals to the current multiplied by the resistance. Okay, then the current is 2 amperes, the resistance is 12. Okay, then it means this is 24 volts. So V across the 10 ohm is also equals to what? 24 volts. Why? Because if we can go and redraw that, we'll get the 10 ohms here. Okay, that's the 10 ohms, which is parallel to the 12 ohms. Okay, right. So in other words, let's call it V1, and then this is V2. Okay, so V1 and V2 are connected in parallel. It means V1 is equals to, so our 10 ohms and 12 ohms are connected in parallel. It means V1 is equals to V2, because we know in a parallel combination of resistors, the voltage remains constant, right? So now that we have the 24 volts, we can find the current passing through the 10 ohm. So the current for the 10 ohm is equals to V over R. Okay, the voltage is 24 volts divided by 10, okay, which is 2.4. Okay, just to verify that, 24 divided by 10, this gives us what? 2.4 amperes. Now, if we can go back to the circuit quickly, how much current passes through the 10 ohm? Okay, how much current passes through the 10 ohm is 2.4 amperes. And then how much current passes through the 8 ohm and the 16 watts electrical device is 2 amperes. So our total current in the circuit, total current is equals to 2 plus 2.4, which is equals to 4.4 amperes. That's the total current passing through the battery. Right. And then now it says determine the internal resistance of the battery. Now what do we have? We have the EMF, okay, which is equals to what? Which is equals to 36 volts, right? Then we can also, because the 6 marks is another multi-step, so we know that we can find the total current. The total current passing through this is 4.4 amperes, right? Okay, which is the total current. So now we want the internal resistance, right? We know that the 12 and 10 are in parallel, as we have shown in this case. So R parallel in this case is equals to 10 multiplied by 12 over 10 plus 12 for any two resistors in parallel. Okay, this gives us what? 10 times 12, okay, which is 120 divided by 22. Okay, this gives us 5.45. Okay, ohms. All right, so we've got the total resistance for parallel. So R total in this case, which is external, is 5.45 plus the 2 ohm, which is in series. This gives us 7.45 ohms, right? Then we know that E is equals to I R plus R, right? We're looking for the internal resistance, which is unknown. So our E is 36, our current total is 4,4, our total effective resistance external is 7,45 plus an unknown internal resistance, right? So it's going to be 36 divided by 4,4, okay? I'm isolating R. This gives us what? 8,18 less 7,45, okay? This gives us an internal resistance of 0,73 ohms, right? So what did we do here? Let's go back to the circuit. What did we do exactly? We found this parallel combination. We know that this is 12. These two in series is 12 ohms. These two, they give us 12 ohms, okay? This is 8 plus 4, okay? That's our 12 ohm, which is parallel to 10. They gave us that resistance of what? 5,45. And we agreed that this one is in series, the 2 ohms. Then from there, we did our substitution, and we used that formula to determine the unknown internal resistance, because we've got the EMF, we've got the current, we've got the external resistance, then we can find the internal resistance in that case, right? Now, having said that, because of time constraints, I think what we begin to appreciate in summary is that in a series circuit, because there is only a single path for current to flow, current will remain the same, okay? Once we appreciate that, we also know that in that very same series circuit, potential difference is divided, right? Then as for the parallel combination of resistors, current is divided while the potential difference remains the same. So with more and more practice, I think it will get to actually become more or less second nature. You become more confident in answering these questions based on electric circuits. So the activity that is shown on your screen, you'll take it as homework. It involves power. It's a parallel circuit. Try that, and then you'll use the opportunity with your teacher to try and do feedback and clarify where you might have gone wrong and possibly learn and improve from that experience. Because of time constraints, this brings us to the end of our session for today. It's cheers and bye-bye. See you soon.